We are in chapter 10. In chapter 10, we're going to talk about one sample tests of hypothesis. Before we actually go take a look at some elaborate examples on how to test hypotheses, let's begin by a definition of what is a hypothesis. So here I have my almost one-liner on what is a hypothesis. A hypothesis is really a claim that we make about the value or values of population parameters. That's all that is. It's a statement of belief. What we believe, what somebody believes the value of the parameter or parameters of the populations are. So for example, where I live, let's say I live around 92111 zip code, and I claim that the average rent, based on my experience living in that neighborhood or in that zip code, in that location, that the average rent for a one-bedroom apartment in that zip code is roughly about $1,500 a month. So there you go. That's an example of a hypothesis. A statement of belief, but this would be my belief. Or here I have another example. The average community college student earns approximately about $120,000 per year. Now, the reason I have some ridiculous number here is because the first example seems reasonable, right? My claim seems reasonable. However, in the second example, my claim is unlikely. So we'll talk more about this later on. But I know that $120,000 per year, that's not a typo. It's just the idea is that anybody can make a claim, right? So it's up to the data to determine whether the facts of the research support or in favor of this statement, or actually they are opposite, or they are not in favor of this claim. Now, every hypothesis has two parts. It's a null and an alternative part of the statement of the hypothesis. So what is a null hypothesis? This is a hypothesis we want to test. We commonly call this the status quo hypothesis. And being a status quo, that means things do not change, correct? When something is a status quo, means it doesn't change. So typically this null hypothesis represents the hypothesis of no change, no difference, and things in that nature in the value or values of the population parameters. So for example, in my two examples I have here, these would be considered the statement of the null hypothesis, because I made this statement and perhaps somebody may want to challenge it, they may want to test it, whether my statement is true or not. So these two are both examples of null hypotheses. Now, the other, before we actually look at the alternative, the symbol that we use for null hypothesis is H for hypothesis, and a subscript. This is the null sign. I know it looks like a zero, but it's like what I have here is this. Like, let's say I want to write the temperature 30 degrees Fahrenheit. This is the degree symbol that you're familiar with, and it's actually called a null symbol. So that's what that is. It's not a zero, it's a null symbol. So this is the statement of the null, the beginning of the statement. Now the other part of the two-part statements in of the hypothesis, the alternative hypothesis, there you go. This is what the researcher actually is trying to show. Okay, so because of that, we often call the alternative hypothesis a research hypothesis. Okay, so the idea here is that the researcher is trying to gather evidence against the null and show or prove that the null is actually not a correct statement. That is, the status quo actually is no longer status quo, and that there has been a change in the status quo. Now this change and we'll see in a few minutes, we can show the disagreement to the null hypothesis in 3 ways. I'll show you those in a moment. But the symbol that you actually see here, down here, these are the symbols we use for the statement of the alternative. All 4 of these are valid. I may use them interchangeably through this lecture. H with the subscript A for alternative, capital R for research, capital A for alternative, little a, cap A, doesn't matter, and H with the subscript 1. In your book, actually your authors use the subscript 1, but again I use these interchangeably. I try to stay with maybe the first and the last one throughout the lecture. Okay, now as far as the null and the alternative go, this might help you. The statement that we make, the status quo, the null, is actually an event that we define. And if we view these hypotheses as events that we define, it turns out that these events are complementary events. So for example, if the null says it's cold outside, the alternative says it's not cold. If the null says something is good, the alternative says it's not good. And so anyway, they're complementary events. Okay, the null and the alternative. So what are we talking about when we say we're doing a hypothesis test? Here's a definition of a hypothesis test. A hypothesis test is just a collection of procedures that will ultimately help us decide whether to reject or not reject the old values in favor of the alternative, the research. So that's what the hypothesis test is. It's just a collection of procedures that help us test statements about the null. Now here I'm going to have some examples of null and alternative together. They're always paired together. For every null there is an alternative. You cannot have one without the other. So in my first example, the null, let's say these different companies are working towards a vaccine for COVID-19. Okay, so whichever the company is, they're hoping to show that their vaccine is effective. So this becomes the statement of the research. The research wants to show that the new vaccine is effective. But the null hypothesis, on the other hand, remember these are complementary events. So the researchers say the vaccine is effective, but the null takes the other side of that. Null presumes that the vaccine is not effective. Okay? This is a case where they're exactly negations of each other. And let's take a look at another one. In the second example here we have the null hypothesis says or reads, the average community college student makes $120,000 a year. Remember, that was my statement of belief. So that's the status quo. The alternative could be any one of, let's say, yourselves or any researcher or anyone, any person, any other person. This is one way to state their alternative, their research, is that they may claim that the average community college student does not make $120,000 a year. Now, they could also say, instead of does not make, they could say they make less than that. Most likely, that's what they want to show, right? We know they don't make that much money. If they did, they wouldn't go into the college. So, but that's the alternative in this example. So, now here I have in chapter 9, actually this is chapter 10, so to pretend that that's chapter 10, actually I can maybe, there you go, erase that one and change that to a chapter 10. In chapter 10 we are interested in testing hypotheses about the mean, so that's what we want to do in this chapter. Okay, now remember, mean, the population means that's mu, the Greek symbol mu, subscript x means the variable, whatever the variable is. This could be the average income, the average home prices, the average height, the average cholesterol level, the average the driving distance, the average speed, whatever the average is. The reason we are so hooked on the average is because we usually decide things based on the average person. What does the average person think? What is the effect of a new policy on the average person? So everything is about the average person or the average subject. So, okay. And so here, there are 3 scenarios here. These 3 ways I have highlighted them in yellow. These are the 3 ways that we can actually show our disagreement toward the null hypothesis. In the first example, but in the first line here, the null hypothesis reads, the population mean is less than or equal to some value of the mean here. The symbolic mu with a subscript, the null subscript looks like 0. This is actually a number. In my rent example, this is 1,500. Community college, this is 120,000. So whatever that is called hypothesized value of the mean. So here's the alternative. Anybody can show their disagreements in the form of one of these 3 ways. They could claim that mean is greater than the hypothesized, or it's not equal to, or is simply less than the hypothesized value. And what I've done on the null side of things, I've made these statements exactly negations, complements of these. So if null says it's less than or equal, the alternative must say it's greater than. If null says it's equal to, simply equal to, alternative must say it's not equal to. And if the null says it's greater than or equal, alternative says it's less than. See how complementary those are. Now, as far as categorizing or classifying the hypothesis test, the one that alternative we have greater than in the alternative is called a right tail test. If it's not equal to, it's called a two-tail test. If it's less than, it's called a left tail test. What does this have to do with the tail? The reference here is to the tail ends of the probability distribution. Okay. And so here, just to clarify things, a mu with a subscript, the null subscript here means hypothesized value of the mean. And we read this as a mu naught. And this is the correct spelling of the naught here, mu naught. And this is how it's written. The null hypothesis in this case is mu equal mu naught. Okay. Now, one thing just to clarify is it is okay, it is safe to always assume the null says mu is equal to. Okay. One thing I want you to note here about the alternative. If you look at all 3 inequality symbols, greater than, not equal, or less than, none of these include the equal sign. Okay. So keep that in mind when you're trying to set up the statement of the hypothesis in the problems or in real life, whatever. The alternative hypothesis will never have equal sign in it. It's not allowed to have an equal sign. By contrast, look at the null. See, all 3 forms of the null have equal, equal, equal. So to make it easy on the students, we usually say assume the null is always equal, equal, equal. In other words, we always take the null to be this middle one, and we allow the alternative to be any one of these 3. Okay. And the reason for that is because, for example, let's say I claim the average speed on the freeway exceeds 70 miles an hour. That's the average, not individual. So if the null says, no, it's just 70 miles an hour, it could be actually less. But if I cannot show that it's equal to a hypothesized value with my first claim, because my position is that it exceeds. So if I cannot show that it exceeds, then equal prevails, let alone less than. Okay, so that's kind of a thought process behind the justification for letting the null always be mu equal to a hypothesized mean. Now, how do we know when to use any one of these symbols? Of course, you look for the keywords. How do I know the alternative is greater than, not equal, or less than? So remember, we look for the keywords in the statement of the exercises. And these are some of the keywords I have. If this statement is at least, at most, no difference, no more, exceeds, etc. Things like that. All of these words translate into inequalities. And again, keep in mind, the alternative will never have equal sign, and we're always going to assume the null is equal. Okay. Now, how are we going to actually go about doing this? So this is the logic of hypothesis testing. There you have it. Okay, so let's say I made a claim. The average student at community college makes $120,000. There you go. I made my statement. So how are you going to go about disproving what I claimed? So your steps are as follows. You're going to get a random sample, probably a simple random sample from the population here. That means from the people that attend a community college. Let's say my focus is all community colleges in the state of California. Or it could be just a community college, a local one, San Diego Community College, Grossmont, Southwestern, and so on. Okay. So we're going to take a simple random sample from the population under investigation. And then we're going to compare the sample values to the hypothesized value. My claim was the average student makes $120,000. So let's say a researcher who really thinks it's less than that, they're going to go get a sample, a simple random sample from a group of community college students. And they're going to come back and they're going to compare the average from the sample to my statement, to my hypothesized value. And then we're going to sort of compare them. And then most likely they're not going to be exactly equal because we're sampling. So the question is, well, how close to the hypothesized value did we come? If we are within a margin of error, then we're okay. We're going to say, sure, the hypothesized value stands. But if we see extraordinary scores, so in the case of $120,000 a year income, if I see $40,000 a year, that's just $80,000 less. So that's not by coincidence. That's not just sampling variation. We're going to say, look, you told me 120,000. My sample shows 40,000. There's something wrong here. This is too much of a coincidence. I have witnessed an unlikely event that could not have occurred if what you said was right, if the population mean was 120,000. So that's pretty much what this paragraph is trying to tell us. Okay. So if our sample data value based on some criterion, oh sorry, I left the E out in some right here. So if sample data value based on some criterion is consistent with the hypothesized value, then we don't reject it. Now the question is, what is that some criterion? We'll talk more about that. Otherwise, we're going to reject the null in favor of the researcher's claim, that is the alternative hypothesis. And also I want to mention that this chapter, by the way, is the most challenging chapter of the course for most students. The topic of hypothesis testing is usually very complicated, highly conceptual. And if you feel like, my gosh, I'm not sure what I'm doing, don't worry, you're not alone. This chapter is the most difficult chapter of the course because it's highly conceptual. But I'm hoping that through these examples, the way I explain them, I can clarify these for you. Okay, so now what is the logic? I mean, I have up here, the logic is what that paragraph reads, but I should probably say not logic, but let's say what is the mathematical basis for what we want to do, right? Everything we do in math, sciences, engineering is based or backed by mathematics, right? Correct? So what is a mathematical basis for the logic of what's stated up here? It turns out that the mathematical engine behind the scenes, if you will, of hypothesis testing is based on proof by contradiction. That's what that is. Very simple, which is a valid way of proving conjectures and assertions and theorems in mathematics. So, and in my example that you're about to see, I made an example from our judicial system. In the US judicial system, in fact, our very judicial system is based on the mathematical proof by contradiction. So, how is this proof by contradiction going to go? Now, for the moment, let's put your justice hat on. Okay, so let's say we're in a courtroom now. So, in our justice system again, the null hypothesis is the hypothesis of innocence. True. So the null says the defendant is not guilty. And look at the alternative. Defendant is guilty. See how complementary those events are? Guilty, not guilty. They have to be complements. And in our judicial system, we always assume the null to be true, no matter how guilty that person might be. Okay, so what happens is the prosecution has the burden of proof. In our work, that means the researcher. The researcher has to collect data and gather evidence for the alternative and against the null. Okay, so that's what I have here. Prosecution gathers evidence against the null. Okay, now here I have a contingency table, and I'll explain how these check marks and what the type 1 errors, what do they mean and where they come from. So in this contingency table, let's say up here I have, this is how I started this table. I started with the labels. So this reads true state of nature about the null. What I mean by true state of nature about the null is this. Remember, we don't really know what the mean of any random variable in the population is. We simply don't, because perhaps the population is dynamic, the population changes, it morphs itself into something else, there are too many subjects, too many people in it, and what have you. So realistically, we don't really know what the average speed is on the freeways. We don't know what the average work day are or work hours are. We don't know on average how many hours people get sleep at night. And a lot of averages we just don't know. So that's what we mean by true state of nature. It means it's what it really is and we don't know. So about the null here. So the true state of nature about the null is that the null is true or is false. Now, reflecting this back to our judicial system, going back to our defendant. True state of nature about the defendant. True, that means the defendant is not guilty. Or is false, the defendant is guilty. But remember, we don't know that. But that's what it is, truly what it is. The defendant himself, herself knows whether they are guilty or not. That's what the true nature is in this case. And here is decision. So let's say the jury comes out and renders a decision. And suppose there's no hung jury here. Suppose they actually come up with a decision, and the decision is to reject the null or not to reject. In this case, I'm saying accept the null. Those are the only two options. So now let's move across the table here. So if the true state of nature about the null is true, that means this person sitting in the courtroom is truly innocent. Not guilty, innocent. See, true. That means that the person is innocent. And the jury comes out, rejects the hypothesis of innocence, rejects the null. They reject the innocence while it's true. Then in this case, an error is committed, and that's not good. So a type 1 error is committed. And in this case, a type 1 error is rejecting the null when the null is true. So in context of our judicial system, that's when an innocent person is found guilty. So that's what the type 1 error is. Next to that, I have a check mark here. Check is the correct decision here. So let's say the null is now false. The person in the courtroom is guilty. The true state, the truth of the matter is that this person is false. Null is false. They're guilty. The jury comes out, rejects the hypothesis of innocence, means they found them guilty or her. So in this case, a correct decision was made. A person had committed a crime and they were found guilty of that crime. That's what we're hoping for. Also, we're hoping for this one. Let's say they arrest someone on a suspicion of something, and they take him to the courtroom, and the jury comes out, and this time they accept the hypothesis of innocence, where in fact the null is true, the person is not guilty. Jury comes out, accepts the hypothesis of innocence, means they found him or her not guilty. That's perfect scenario again. And everybody's happy probably. So a correct decision is made. And lastly, in this cell, another kind of error is committed. A type 2 error is committed. A type 2 error, therefore, is the error of accepting the null when in fact the null is false. So we're back to a situation where null is false, means the person is guilty. But the jury comes and accepts the hypothesis of innocence. So they found this person not guilty while this person was guilty. So maybe for some reason they just, maybe that defendant had really a good attorney. That could be one possibility. Or jury just did not have enough evidence to convict the person. But anyway, that kind of error is not good either. So, all in all, when you conduct any hypothesis test, there are two types of errors that we can commit. We can commit a type 1 or a type 2 error. Okay, so I went ahead and wrote down what a type 1, type 2 error is now. So remember, the table helps me sort this out. So if you make up this table on your own without looking at this, that would be great. So you might want to copy the margins, but just leave the body of that table in the cells blank and kind of argue your way through. But type 1 error, we're going to call that error of rejecting a null hypothesis when in fact it's true. And type 2 error is accepting the null or failure to reject it when in fact it is false. Now, symbolically, the probability of committing this kind of error, we're going to call that alpha. And probability of committing this kind of error, we're going to call that beta. And because these are probabilities of events, they both must be between 0 and 1. Now, going forward, by the way, we are only going to focus on alpha, probability of a type 1 error. We're not going to do anything with type 2 error, although it's there, but we're not going to do that. Okay, so now in chapter 9, when we talked about confidence intervals, remember we talked about alpha? In chapter 9, alpha was not a good thing, right? Remember we called alpha the uncertainty level associated with the confidence interval. So alpha, that's exactly the same alpha that it was in chapter 9. So in chapter 9, alpha was a bad thing. Here it's a terrible thing because, again, incorrect decision could be made. So alpha is called probability of a type 1 error. And also alpha is called or known as the size of the test. And alpha is called the stated significance level of the test. So what's going to happen now is this. How do I calculate this alpha? There is nothing to calculate. Alpha is actually stated. Notice I have underlined the word stated. So something that you and I, or the researcher, actually determines ahead of time before we conduct the hypothesis test. So, for example, let's say I'm gonna decide, or we're gonna decide on, let's do alpha 05. The typical values I have here. If not, let me write it down here for you. The typical values of alpha are alpha 10% or 5% and 1%. There you go. Remember, error is bad no matter who suffers as a consequence, whether a person is incorrectly convicted of a crime or a guilty person is set free. Okay, both cases are bad. So we want to minimize this number. So that means the smaller the alpha, the better. 10%, 5%, 1%. Now, as we lower the alpha, by the way, because these, as you will see in a minute, these are areas in the tail end of this distribution. So as we go from 10 to 5 to 1, we are pushing out into the tails of the distribution. So it is harder to reject the null. Okay, as alpha drops, it is harder to reject the null. So you're setting the bar pretty high. Okay, and again, alpha is a stated significance level. In the statement of the problem, usually alpha is given, like test the hypothesis at alpha whatever, like 0.5, 0.1 or 0.1, which is 5%, 1%, 10%. So, and I have here, remember, keep in mind, alpha is a bad thing. Okay. Now, in our court examples, I already mentioned it, but I went ahead and wrote it for you also. So what would be a type 1 here? The case is where innocent person is found guilty. And a type 2 is when the guilty person is set free. And one other thing is we often hear or talk about result being statistically significant. So what does that mean when they say the result of the experiment was statistically significant? When I hear those words, anytime I read it in a journal, or if somebody through research community tells me, oh, the result of something was statistically significant, to me that just tells me right away somebody rejected a null hypothesis. The status quo no longer holds and it was changed. So that's what it really means. Okay. So when we say results again are statistically significant, means we were able to reject the null and we actually changed the status quo. Okay. So how are we going to actually test hypothesis? Now remember, we're going to use megastat, right? So I'm not going to show you these formulas at all. And in megastat, it's really easy to do, but we do need to know what it is that we are finding, and the interpretation and the conclusion is what we're really after. Okay, so don't worry about the details of the formulas. So how are we going to actually test these hypotheses? Well, there are two approaches, and that's what this part is. There are two approaches to hypothesis testing. One is called critical value, the other one is p-value. In megastat, our focus is going to be on p-value. Okay, and that's what realistically in the research gets done. Everything is based on p-values. We seldom look at critical values. But I'll go over both of them. But again, keep in mind, please, our focus is on p-value. With critical value, this is the criterion that we mentioned earlier when we talked about the logic of hypothesis testing. We said this is a set of procedures that actually decide to whether to reject or not reject a null based on some criterion. So this is the criterion. So the critical value is our criterion as to whether to reject or not. So, and that's why it's called critical, because if we see a value that exceeds, again, it's all based on margin of error. and really standard deviation, how far away we are from the center. If we are, for example, over 2 standard deviation, that's my critical value. That's 2. Could be 2 or -2, depending on whether I have greater than or less than position or interest in the hypothesis. Now, so I'm going to call the critical value as the cutoff point for how far the sample mean can be from hypothesized before it is judged to be significant. Okay, so in that sense, it's critical. It's the cutoff for significance versus not significance. Now, where do these critical values come from? Well, they depend on alpha, the probability of a type 1 error, and or the size of the test. That's where they come from. Okay. And what this critical value is the distance from hypothesized mean expressed in terms of standard units or standard deviation away from the mean. Okay. That's what the critical value is. So here I have an example before we actually look at this shape. And by the way, we're going to assume that we're sampling from a normal population throughout the entire chapter here. And if we're not sampling from a normal population, we assume the sample size is large. And we're going to actually look at the case where population deviation, sigma, is known or unknown, just like in chapter 9 with the confidence interval we did. Okay, now let's take a look at this example. Let's say the alternative is mu is greater than 50. Okay, so that's what the alternative is in this case. Mu is greater than 50. The null says the mean is 50. So here's how we're going to settle this. Assuming normality, the center of the distribution is the hypothesized value. Remember, we always assume the null is true, just like our judicial system. That's the premise. That's the foundation of proof by contradiction. That's how we started. So for example, if I say 2 plus 2 is 10, based on proof by contradiction, you're going to say, okay, well, sure. Okay, you're right. 2 plus 2 is 10. So I'm going to grab 2 apples and then 2 more apples. I'm going to combine them. And how come I'm seeing 4 apples, not 10 apples? See how simple that was? That's really the gist of it. Proof by contradiction. So same thing with our data. We assume the null is true. Remember, the null is this. We assume mu is 50. Okay. So, and I'm going to set my cutoff at 2 standard deviations. See right here? I decided on that. That's why this 2 standard deviation depends on the researcher. Okay. So, there's the hypothesized mean, and my cutoff is 2 deviation. And I think it's greater than, see right here, I have mean is greater than 50. So that's my statement of belief. Therefore, my cutoff is anything that is 2 deviation or more, I'm going to judge the result significant. Okay, so there's my cutoff. That's my critical value. So in the red zone is anything above 2 deviation. Okay, and in this red region, we're going to reject the null hypothesis. I'm giving this much under the distribution. Everything less than 2 deviation on the positive side, I'm going to give that to the null. So for example, whatever deviation, I didn't make up a deviation here, but let's say if each deviation is 10 units. So if I see here is 50, 60, 70. So if I see a score of 70 or more, I'm going to reject that it's 50. If I see 60, yeah, that's close enough to 50. If I see 54, close enough. If I see 40, close enough. 30, close enough. Because see, my interest isn't greater than. So this is what my concern is. I don't care about the rest of the distribution. Okay. And again, I arbitrarily set that to standard deviation. Just want to point that. So other researcher may say, well, my critical value is going to be 3 deviations. Somebody else says, no, 1 deviation. The greater the critical value, the higher the bar, the shorter this, the smaller this rejection region, and it's harder to reject that null hypothesis. Okay, so I mentioned about it. So again, we're giving with 2 deviation cutoff, we're giving everything below that benefit of a doubt, I call it, to the mean. Okay, that the difference between the sample mean, population mean is just sampling error. Okay, so here we're going to define rejection, non-rejection regions, and critical value. So remember, rejection region is the value of the test statistic that leads to rejection of the null. Now, what is a test statistic here? Think of your test statistic as your jury. Okay, test statistic is going to be a value that is based on sample mean. Okay, that's what that is, our test statistic. Megastat will do all this for us. The non-rejection region, of course, is the region where we don't reject the null. See, rejection region, we reject the null. Non-rejection, we don't reject. And the critical values are cut off. It's the value or values of the test statistic that separate rejection, non-rejection. In that sense, that's why it's critical. And here I have my test statistic, because again, in here it talks about test statistic over and over. This is a value that's calculated from the sample data. And it's going to be a statistic for us. That means it's going to be calculated from the sample that we use to test the hypothesis. So we're going to have a formula, but remember, we're not going to look at these formulas because we go to to megastat. And also remember, this is critical value approach. I said we don't want to do it this way, but it's in the book, so I mentioned it. So here in this drawing, let me not show you the whole thing. In this display, what's going on with this? If the alternative says the mean is different from a hypothesized mean, two-tailed test, see, we have 2 rejection regions. And these are the cutoffs, the critical values. So we have 2 critical values for the two-tailed test. If the alternative is less than, then the rejection region is on the left tail. That's why it's called left tail. The again reference to the tail here is where the rejection region is. If the alternative is greater than, the rejection region is on the right side. Okay, so that's what these are. Now I can take these extraneous drawings out. And this one, it's not cooperating. There, now it is. Okay. So hopefully you follow this drawing then. Now the significance level, or the test size of the test, alpha determines the critical values. And what we're doing is we're doing a z-test, just like we were doing with the confidence intervals. We had a z confidence and t confidence. That's exactly the same thing we're going to have here. If sigma is known, we do a z-test. If sigma is unknown, we do a t-test. And there you go. So we're going to reject the null. And this is to show you where the critical values are. You see that? Alpha, remember this z sub alpha business we're looking at? It's coming back here. So your critical value, again, these are your critical values. All of them depend on alpha, which is the size of the test for all of them. Okay, and I guess that's good. Megastat will give us these cutoff points, the critical values. But here are some important values of z sub alpha. We've seen these before, but I just want to echo again right in here what they are. So for example, if alpha, let's say I'm doing, just to show you something here, let's say I have, this is a standardized z distribution, 0. So let's say I'm doing a right tail test. Right tail test, that means I'm doing something like this. Okay, a right tail test. If I'm doing a right tail test, and this is, let's say, alpha 0.05, then the value of that, the critical value, is 1.645. There you go. So if my standardized, the z-score, my test statistic will give me a number. That's going to be a z-score. That's what our test statistic gives us. It gives us a z-score. So if that number is going to be 1.645 or more, we're going to reject the null. Okay. And that's all that is. Again, Megastat will give us these critical values. Now, let's take a look at the other approach, which is a much better approach. One thing, by the way, one thing this critical value approach does not do, it doesn't tell me the strength of the evidence against the null, how strong of an evidence we had, whether we rejected it or not rejected the null. We couldn't do that with critical value approach, but with p-value approach I can actually do that. I can assess the strength, or quantify, I better say, rather than assess. I can quantify the strength of the evidence against the null. So that's what this p-value approach is. Now the p in p-value, or what do we mean by p-value? P in p-value is probability. That's all that is. So again, your p-value, just so we know, p-value is going to be between 0 and 1 because it's a probability. Okay. Now, there's so many ways to define this p-value, but here's one way to define p-value. P-value tells me the probability of getting sample values as extreme or even more extreme than the ones we just got if the null was true. So for example, let me go back to my community college students. Average $120,000 a year. Okay. Let's say I'm going to get a sample. Most likely the sample is going to be about $20,000 to $25,000 average, right? Maybe 30, that's a stretch. About $20,000 to $25,000 average. Then what p-value in my example will give me is that how likely was it to get a sample average of $20,000 to $25,000 if the null was true and the average in the population was in fact $120,000. So that's what this phrase is trying to get across. Okay. Here's another way to define p-value. P-value, remember I mentioned, quantifies the strength of the evidence against the null. And how does it do that? I'll show you a table in a moment where a range of scores for p-value. I'll show you how it quantifies it. Now, alpha, remember alpha was a stated significance level, the size of the test. So alpha is a stated significance level, while p-value, because it's actually based on data that we collect. So p-value is called the observed significance level of our hypothesis test. So remember, alpha is a stated, whereas p-value is the observed. Both of these are significance levels. One from data observed, one from the researcher just stated. So for that reason, the observed significance level, we shorten that to OSL. That's what p-value is. Some people call p-value OSL, observed significance level. Now, here's our decision on when to reject the null hypothesis. So this we want to know, folks. This is important. In testing any hypothesis, regardless of the parameter of the population, at all levels of research, this is true. Our decision rule towards the null, we're going to reject the null if p-value is going to be less than or equal to alpha. If somebody gives us an alpha, typically in our textbooks, in academics, in classrooms, alpha is going to be given, so this boxed in statement makes sense. In real research, if you do real research, or some of you may have or will be, or you're in the midst of doing it, but anybody who does research, no one's going to tell you use alpha 05. With p-value, typically we let the data speak for itself. Okay, and I'll show you how it speaks for itself in a moment. And okay, so I need to actually show you a table for p-values. When I said that we let the p-value, the data speak for itself, the evidence, let me show you that. Okay, so there it is right in here. You see this is it reads, these are the guidelines for using p-value to assess the evidence, which I call to quantify the strength of the evidence against the null. So with p-value, if our p-value is greater than 10%, and again, Megastat will give us p-value. Don't worry about how am I going to calculate it. You're not. But if the number we see is greater than 10%, the evidence against the null is weak to none. For p-value between 10 and 5%, exclusive of 5, inclusive of 10, the evidence is getting stronger. Now it's only moderate. For p-values at 5% or lower, up to 1%, from 1 to 5, the evidence is strong against the null. And if you do a research, the software comes out and shows p-value less than 0.01, that means you have very strong evidence against the null. And there you go. So this is what I meant by letting the data speak for itself. Okay. Now, let's take a look at actually an example here. Okay, and then we actually go to Megastat with this example. And then we'll transpose the results to here, to my note. Let me just slide it up. There you go. Okay. So let's read on this example. A company manufactures and assembles desks and other office equipment at several plants. The weekly production of these follow a normal distribution with a mean of 200 and deviation of 16. Notice here we are given sigma, right? Deviation, that's sigma. Sigma is given. Let me actually activate my pen. There you go. See, sigma is 16. In this case, sigma is known. When we know sigma, we use a z-test. Okay, keep that in mind, please. Now, recently, due to market expansion, new production methods have been introduced and new employees hired. The VP of Manufacturing would like to investigate whether there has been a change in the mean weekly production of desks and other office equipments. Use 5% significance level. You see that? There's your alpha. Because it's stated, we're told it's 5%. So that's the stated value. Use 5% significance level to test the hypothesis. The average number of desks produced in a 50-week period was 203.5. Okay, so in a 50-week period, that gives us indirectly the sample size, right? Each week represents one observation. So 50 weeks, That means n is 50. Okay, and so notice when I set up this statement of hypothesis here, this hypothesis is going to be a two-tailed test of hypothesis, and I have it in yellow here. The researchers want to know if there has been a change. It doesn't say more or less in the way of production. It doesn't say they're making more or fewer desks. It just says, has there been a change? Because we don't have a direction, we're going to take alternative to be not equal to. The null says, look, it's 200. No, there has not been a change. Remember, status quo. The null says, no, there is not a change. But the alternative, because we don't have a direction in one way or another direction, we're just going to go not equal to. Okay. And now we're going to go to Megastat and actually do this. So these are weekly production. Okay. So let's go to Megastat and do this exercise. Okay, now I am in Megastat. So here's my add-ins. So please, here's your step-by-step. Add-ins. You go to Megastat. Okay, and as I do this, if you want, feel free to pause the video and make notes on the steps yourselves. But it's pretty easy to follow, self-explanatory. Everything is really descriptive here, what we want to do. So we go Megastat, and we're going to hypothesis tests. Okay. Now, in this chapter, we're doing mean versus hypothesized value. See? We are not doing comparing two groups. We are not doing paired. We're not doing proportions. We're not doing any of these. This is all we're doing in chapter 10. So click on that. Left click once. And this is our dialog box, the pop-up that comes. Now, for this example I have, you don't see the data, right? We don't see those 50 weekly production figures. So we don't have data input. I'm just going to go summary input. Now in the summary, notice when I selected it, the active cell is here, your input range. Megastat is expecting a range of information, not the data, but information, the statistics, if you will. And it's telling me what it's looking for. It says, okay, select the range. That would be in our spreadsheet, which is blank right now. Select the range with label. The label is usually your random variable. So in this example, it's going to be weekly production. So, and it has to be in this order, by the way. They want label, and then they want the mean. Okay, that's the sample mean. Okay, and then the standard deviation, which is your sigma. Okay, and the sample size. It has to be in that order. Okay, so all right, so right now, because my spreadsheet, you can see I have nothing here. So I need to actually create these before I can run this procedure, which is good. You're actually gonna watch this getting done. Remember, the order is label, mean, deviation, n. Okay, so here we go. I'm gonna type in label, mean, deviation, and n. Label, mean, deviation, n. That's what it was looking for, right? Label, I'm going to put label as weekly production. Okay, that's the label. The mean, that was a sample mean. The sample mean, I believe, was 203.5. That was the last part of the problem. The known deviation was 16. And the sample size was actually sample size 50. And there you go. You see that? So now we are in a position to run Megastat. So I'm going to go add-ins, Megastat, hypothesis test, first selection. There you go. Now let me slide this over so you can see. I'm going to click on summary input. See, these are summarized. You don't see the data. And I have, see, label mean deviation n, label mean deviation n. That's exactly the order in which they appear. Click on input range. Left click. All the clicks are not double click, single click. And now left click and hold and drag once. Once you drag it to the bottom, let go of the left click. You see, the broken line around those cells means that range was selected. And you can also see it in here. You see that? Hit enter. And there you go. Now, what is the hypothesized mean? Remember, the hypothesized mean was 200. So just type 200. And the alternative, see, remember we only have one of these three alternatives for this exercise that we're doing, not equal. And look at the choices, see, you're doing either a z or a t-test. How do I know which one? You're doing a t-test if sigma is unknown, population deviation unknown. You're doing a z-test if sigma is known. So I'm going to click on z-test because sigma was given. And look in here, you can even get a 95% confidence interval if you want. So I'm good, I'm just gonna hit OK. And there is the output tab. So hypothesis test. Some of these right in here, these are the echoes of what we put in, right? But these are new information. The standard error, that's sigma over square root of n. If you, let me show you, equal, if you divide standard deviation, that's sigma, divided by this QRT means square root of sample size 50. There you go. I'm doing central limit theorem, sigma over square root of n. 2.262742. You see that? If you double click here, you see exactly what I did. So that's what this is. Okay. Now, down below are the two approaches to hypothesis test that I mentioned. The Z here is going to be the critical value approach. So this is actually the Z score that's calculated from the sample. Okay, it's not a critical value. This is the Z score. In other words, what the software did, it says, okay, well, you observed an average 203.5. So it standardized this number. If you subtract 200 from this, you get 3.5. Divide 3.5, okay, by the standard error, by 2.263, you're going to get that. But again, you don't need to know how this was done. But this is all I want you to know, folks. There you go. That's all I want you to see. And that's all that's going to stay with us right here. See. So our p-value for a two-tailed test is 0.1219. 0.1219. So I'm going to copy that into my note now. Okay. You see how that worked? So let's go back to note. Okay, so here we are. You see that I just went ahead and typed this in. Remember, the p-value was 0.1219. Let me real quick go there. Yeah, 0.1219. Okay. So since p-value of, that's 12%. 0.1219, remember in here, p-value, I'm looking at right up here. If p-value is greater than 10%, the evidence is weak, right? P greater than 10, weak or no evidence. So this isn't strong data against the null, because p-value is not less than 5%. we fail to reject the null hypothesis. And our conclusion is that there has not been a change in the weekly production of desks and other equipment. Left the T out. And other equipment. Okay. And there you go. That's what a typical hypothesis test looks like. All right. Now let's take a look at our second example. Second example, we actually have data for it. See right in here. All of this is actually a data that's given. So let's read on this one. In this example, suppose a researcher is interested in testing a hypothesis about the average commuting time in minutes to work. This is one way in San Diego. A simple random sample of 12 commuters are selected and their commuting times and minutes are recorded. Assuming the population deviation is 5.124, the researcher wants to test the hypothesis that the average commuting time one way in the city of San Diego exceeds 30 minutes. That's what they wonder, if it takes people longer than 30 minutes one way. I don't think that's true. One way, well, maybe for some. Okay, use 0.5 significance level. Now something, just so we use a t-test, let me actually change this problem right now. Instead of the word population deviation, I'm just going to say assume the sample deviation. Actually, that's going to mess everything up. Let me, in fact, remove this assumption altogether. And the reason is this. If I remove that, see, I no longer know the sigma, right? I want to do a t-test because we just did a z-test. We want to do a t-test. Okay, so that's good. I'm glad you just saw me modify the problem. So let's just say the researcher wants to test the hypothesis that the average commuting time is 30 minutes. It exceeds, there's a keyword, exceeds 30 minutes. See that? Bold, underline it. Those are the keywords we look for. And of course, our stated significance level is 0.5. That's our alpha. So notice in here, nowhere mentioned now that sigma is known. So we're going to use a t-test. Assume the population distribution, however, is normal. The assumption of normality allows us to use normal distribution. Oh, for this one would be t-distribution. Anyway, that's just our ongoing assumption. So I'm going to actually set up the statement of hypothesis. The word exceeds means greater than, right? There you go. So that means the alternative has to be greater than. That's where this comes from. Exceeds means greater than. So the null, we always take it to be equal. So null says mu is 30 minutes. And with this, we're going to go to we're going to go to Megastat and try to do this. Okay, now notice this time we actually have our data. Okay, so let's go to Megastat. Okay, so I'm in Megastat now. Okay, and I have the time, all the time. These are times, the 12 commuting times one way in minutes. Okay. Notice I don't have summary, I have raw data. So let's go to add-ins, Megastat. Again, we go to hypothesis test, mean versus hypothesized. Now this time I'm going to use data input. Remember before I clicked here and we put all this information? I'm just going to go data input because we actually have the data. And here, left click on input range. Now, it's expecting a range. Left click and hold once and drag. I included the label in there. You see that? Time. And the dotted, all this around the border around the cells is broken line or dotted broken line. That means that's my selected range. Hit enter, and there we go, the range is in here. What's the hypothesized mean for this exercise? The commuting. Remember that we want to know if it exceeds 30 minutes. That's my hypothesized mean. The alternative was greater than, right? Exceeds. And right in here, you see, Z or T. We're going to click on T, because sigma is unknown. And hit OK. And there you go. So, right here. Again, portion of this, the 30 hypothesized mean, we put that in. Everything else, the software figured it out. Megastat figured it out. So the average time is 26.333 minutes. Right? That's the average time for those 12 commuting times. So it's definitely less than 30 minutes, huh? The average, that is. The question is, this difference of almost 4 minutes, is that really a big deal? Is that statistically significant? Although it's 26, is that, remember, we want to know it's exceeding, so this isn't going to look good for us. And just skip all of these, you just go to right down here, p-value. Remember, it all amounts to a p-value. And this p-value approach is going to stay with us, by the way, in our future chapters. So it's a good thing that we're talking and doing it this way. Wow, look at that p-value. Very high, very high. And in fact, see, with 26, we are on the left side of the normal, this to the left of the mean, where our rejection region is to the right side because it's the right tail test. So, 0.987, we definitely have no evidence against the null. The null says, see, I told you it's 30. If anything, it's less than that. But our position was, we want to show it's greater than, and it's not. 0.987. Let me go back to my note. Okay, so here we are. Since the p-value 0.987 is not less than, again, 0.05, our significance level, we fail to reject the null. So what are we going to conclude? See, we failed to reject this. The researchers were hoping for this. They could not gather evidence for it. The null said, see, I told you, it doesn't exceed. The status quo holds. The average commuting time one way does not. It does not exceed. Maybe I just highlight, boldface, underline, all of the above. And there you go. Okay, but whatever it is, it does not exceed it. Okay. And that's how we test this hypothesis. So anyway, so we're good. We're done with this chapter. Sorry, the video took long, a little over an hour. I tried to keep them around an hour. But again, hypothesis tests are the most confusing, most conceptual portion of this course. But here's what's going to happen in the future. In every chapter, we're going to test hypothesis. And now that you're familiar with the idea of hypothesis, the future chapters are going to be much easier. We just change our procedure in the megastat. What's going to be different is our parameter. Instead of x bar, it could be proportions, it could be deviation, it could be whatever. But the whole idea of hypothesis test is going to stay with us now until the end of the course, even when we do regression and correlation. Okay, so with that, we are done with this lecture, and hopefully you followed everything. And again, keep in mind to please take things step by step. As we go through megastat, feel free to pause the video and write the steps down. But again, you just saw me doing this. 2-3 steps is max. That's all you got to do to get to where you want to get to. Okay, so we're done with chapter 10, one sample tests of hypotheses.